to Mr. Tom Creasy.
Thank you, Courtney. Good day. As Chair of the TRB Highway Capacity and Quality of Service Committee, I'd like to welcome you to this second in a series of 8 webinars dedicated to implementing the new Highway Capacity Manual 6th edition. Today's webinar, Bringing Back of the Envelope Back, introduces the new Planning and Preliminary Engineering Applications Guide to the HCM. This document was published separately as NCHRP Report 825, but is considered to be part of the new HCM 6th edition. The guide is the culmination of much discussion and effort over many years to provide guidance to planners, engineers, and decision makers on use of the HCM for planning applications. We on the committee, especially those of us practitioners who have used the HCM for planning, are excited about the new HCM 6th edition and the Planning and Preliminary Engineering Applications Guide. Again, welcome, and I hope you find today's webinar of great value to you and your organization. So let's get started with Aaron Elias.
Thank you, Tom. Before jumping into the presentation, it will be useful to define what planning and preliminary engineering are in an HCM context. Planning in the HCM is generally directed toward broad issues that involve analyzing a large number of facilities. The purpose of the HCM planning analysis may be to identify facilities that have existing or future operational issues for a more detailed analysis. In this case, HCM methods are used to screen out facilities that are unlikely to have problems, allowing analysis resources to be focused on potential problem areas. HCM planning analysis techniques are also applicable to statewide performance monitoring, where the performance of a large number of facilities needs to be summarized without the time and expense of a detailed HCM operational analysis. Preliminary engineering analyses support moderately detailed issues, such as identifying the required number of lanes to provide a given level of service, and conducting a more detailed analysis of a limited set of alternatives. These types of analyses can also investigate the potential effects of proposed system-wide policies, such as lane use control for heavy vehicles, freeway ramp metering, intelligent transportation systems, and the use for demand management techniques. With planning in the HCM context defined, we now move into an overview of the Planning and Preliminary Engineering Applications Guide, which we will generally refer to as the guide for the remainder of the presentation. We'll first cover why the guide was produced. The Highway Capacity Manual is commonly used by transportation agencies to evaluate the current or forecasted operations of roadway facilities. Less well known is that the HCM can also be used to cost-effectively and reliably support agencies' planning, programming, and management decisions. We conducted a survey of practitioners a few years ago as part of an NCHRP synthesis to determine how the Highway Capacity Manual is and is not used for planning. We found during this survey that less experienced users of the HCM are less likely than more experienced users to use the HCM for planning applications. Even when the HCM was being used for planning, it was often only used for short-term planning rather than long-term. These results suggested additional education was needed to inform users on the potential benefits of and how the HCM could be used for planning applications. This corresponded with a participant survey where the #1 desired improvement requested was the development of a planning and preliminary engineering guide. Other desired improvements included travel time reliability measures, better integration of the HCM with travel demand models, and guidance on estimating system-wide measures of effectiveness such as vehicle hours or person miles of travel. It should be noted this survey was performed a few months before the release of the HCM 2010. Throughout its 65-year history, the HCM was focused on describing and demonstrating computational methods for evaluating roadway operations, along with explaining the theoretical concepts underlying the methods. Specific to planning, HCM chapters provide tools such as default values, service volume tables, quick estimation methods, or a combination of these. Although the HCM provides sections in each chapter outlining an HCM method's potential use in operations, design, and planning and preliminary engineering applications, the HCM only provides limited guidance on how to apply its methods and tools in the context of a broader decision-making process. In other words, the HCM is good at describing how to compute its methodologies, but only has limited guidance on determining which methods to use for a particular study. To address the need for guidance on how to apply the HCM in the context of a larger operations or design study, the HCM Applications Guidebook was developed in 2006. This guide is available as part of the online HCM Volume 4, which can be accessed for free after registration at www.hcmvolume4.org. The HCM Applications Guide presents 6 case studies, each of which focuses on a common HCM operations or design application. Each case study, in turn, consists of several problems that address individual issues that might be analyzed as a part of the transportation study. Unlike the HCM, which provides an example problems for the purpose of demonstrating how to perform a method's calculations, the HCM Applications Guide case studies focus on the process, where to obtain data, how to deal with missing data, and how to interpret and apply the results. It was thought that a similar guide on applying the HCM to planning and preliminary engineering applications would also be beneficial. Therefore, National Cooperative Highway Research Program Project 722 was funded to develop a planning and preliminary applications guide to the HCM that would describe how the HCM could be applied in a wide variety of planning, preliminary engineering, and performance measurement applications. This guide was to include, but not be limited to, describing use of default values in service volume tables, how the HCM could be used in scenario planning, how to use the HCM in conjunction with travel demand, noise, and air quality models, and how to evaluate overcapacity conditions in a planning context. The result of this project was the Planning Preliminary Engineering Guide, which can be found for free by Googling NCHRP Report 825, but it will also be included in the online Volume 4 of the HCM 6th edition. We'll now move on to reviewing the scope of the guide and how it is structured. Planning and preliminary engineering covers a wide spectrum of possible levels of analysis. Visualize a plane flying at various altitudes. At a high altitude of 35,000 feet, a plane passenger can see a great distance, but details on the ground below are difficult to distinguish. This is typical of an area-wide sketch planning or screening study, where there is relatively little data, but a large number of facilities to analyze. As the plane descends in altitude, the passenger cannot see as far, but what they can see is more detailed. This medium-level analysis is typical of an HCM methodologies where we are using a mix of both measured and default values. At the lowest level, we have microsimulation analyses, which produce the most detailed results, but are usually geographically limited. Similar to the various levels of a study that can be performed, the precision of a performance measure can vary based on the method used in its estimation. The most precise measurement is usually direct field measurement. For example, I work on a congestion management program in Silicon Valley that directly measures freeway density through the use of aerial photography. When it is impractical to directly measure performance measures in the field, such as the aerial photography, the guide takes the perspective that the HCM analyses using field measured input is most accurate, followed by the HCM analysis using a mix of default values and field measured input, followed finally by the alternative analysis methods described in the guide itself. The guide, therefore, focuses on mid- and high-level analysis methods that either apply the HCM directly or are HCM-based due to applying simplifications to a method described in the HCM to make it more usable in a planning context. So where does the guide fit into a project's life cycle? Generally, the methods described in the guide would be used to help identify the need for a project. Once the project need is determined, the guide can then be used as a precursor to help focus the analysis that will be performed using the HCM itself as part of the project clearance and design phases. Finally, the guide can be used after design and construction is completed to monitor how well the system is working. As the system begins to break down again over time, the guide can assist in determining the need for another project, restarting the cycle again. Given the broad range of potential planning and preliminary engineering analyses, the target audience for the guide is equally large. It includes all current HCM users, but also planners and modelers who have not traditionally used the HCM, since many planning models can use pieces of the HCM as inputs into the model, calculations within the model, or post-processing model outputs. Another target audience are university students in transportation engineering and planning programs, as it provides a good overview and introduction to HCM methods while keeping it simple enough to use in a classroom setting. Recognizing the breadth of the guide's target audience, the guide has been structured so that it can be approached in different ways. Importantly, the guide is not intended to be read cover to cover, but used as a reference book for the particular type of analysis you are trying to perform. Non-HCM users are anticipated to access the guide via Part 1. Those already using the HCM are referred to appropriate parts of the guide directly from the new HCM 6th edition. In addition to providing an overview of the guide, Part 1 addresses topics cross-referenced throughout the guide. Part 2 is divided into sections corresponding to HCM system elements, such as freeway facilities or signalized intersections, and also provides sections on multimodal analyses and truck level of service. Part 3 provides guidance on extending the HCM to larger study areas, including corridors, areas, and entire transportation systems. Finally, Part 4 provides 3 case studies demonstrating how to use many of the methods discussed in the guide. I'll now cover the overview part of the guide before handing things off to Paul to wrap up the discussion with medium and high-level analyses, as well as the available case studies. To avoid confusion with the HCM's volume and numbered chapter structure, the guide is organized by parts and lettered sections. Part 1 contains 7 sections labeled A through G. Section A provides an introduction to the guide. Sections B and C are the gateway to the guide for planners and modelers not currently using the HCM, while sections D through G provide reference information used throughout the rest of the guide, such as default values and service volume tables. Section A provides an introduction to the guide, including describing its scope, audience, and intended use. As I've already covered these topics, we won't go through them again. Section B is the gateway to the guide for planners and engineers working on project traffic and environmental impact studies. It describes the general process used to complete these studies, the typical analysis tools used, and typical data needs. It then provides a table that lists typical analysis tasks for project traffic and environmental impact studies, and points the reader to appropriate sections in the guide where HCM-based analysis tools for performing these tasks are described and illustrated. The section concludes with an introduction to default values, which are standard input values to HCM methods for use when an actual value is not known, such as saturation flow rate at intersections. This table in Section B shows the types of medium-level analysis tasks where the HCM may be applicable. Tasks include preparing inputs to other tools used in the project, such as travel demand models, microsimulation tools, and air and noise models. They also include where to find locations and estimating specific operation performance measures, such as volume to capacity ratios, delay, queuing, travel time reliability, and multimodal quality of service. The table cross-references Part 2 and 3 sections where planning level methods are described, along with Part 4 case studies where the methods are demonstrated. If you want to estimate delay, for example, Part 2, Section H through N, will provide an overview of the planning methods that can be used, while Case Study 2.4 provides where this can be applied through an application. Section C is a gateway to the guide for planners and engineers working on screening and scoping studies, long and short-range area-wide transportation plans, and system performance monitoring tasks. Similar to Section B, this section provides tables describing typical analysis tasks with cross-references to appropriate sections of the guide, providing methods and case studies. This table from Section C shows which screening and scoping tasks that are addressed by the guide. These tasks include identifying potential level of service hotspots by mode, identifying potential capacity problems for the automobile or motorized vehicle modes, and preliminary evaluation of improvement alternatives according to their effects on each travel mode. If you are trying to locate a truck problem areas on a 15-mile freeway corridor, for example, you can use the guide to focus your analysis on a few trouble spots using methods described in Section P. This will be more efficient than analyzing all 15 miles of freeway using an HCM operational analysis. Area-wide transportation planning tasks addressed in the guide include preparing HCM-compatible capacity and free flow speed inputs for inclusion into travel demand models, applying HCM-compatible volume delay functions to estimate congested speeds, and post-processing travel demand model outputs to estimate specific operations performance measures. Performance monitoring of the federal aid highway system is a requirement that was introduced by the MAP 21 Federal Highway Bill. The HCM analysis techniques that are relevant to MAP 21 goal areas of congestion reduction, system reliability improvement, and freight movement. The guide can assist with system performance monitoring by providing techniques to estimate speeds, capacity, congestion, reliability, and other performance measures. If, for example, you are monitoring a freeway as part of MAP 21 requirement and are interested in estimating freeway speeds, Section R5 of the Part 3 represents planning level methodologies that can be used, while Case Study 3.2 demonstrates an application of these methods. Section D describes methods for working with traffic volume data, both actual counts and estimates produced by travel demand models. This section recognizes that transportation agencies may have already established specific traffic forecasting and analysis policies. In these cases, the guide recommends that analysts remain consistent with those policies. Therefore, the guidance provided in this section can be applied in the absence of agency policies or be considered when agencies update their own policies. Analyzing the operation of an urban street using HCM requires some knowledge that the type of traffic control that is needed for each intersection. In a planning and preliminary engineering analysis, these decisions may not have been made yet, or the purpose of the analysis may be to determine the form of the traffic control needed for future conditions. Section E provides methods for predicting what the intersection traffic control may be, based on major and minor street traffic volumes and the directional distribution. For example, if the major street has a traffic volume of 800 vehicles per hour in both directions, and the minor street that it's crossing has a traffic volume of 400 vehicles per hour, then the most appropriate traffic control type is likely to be an all-way stop or a single-lane roundabout. A common complaint about the HCM methods, particularly in a planning context, is that they require too much data. Default values are a means of reducing an HCM method's data collection requirements while still producing reasonable analysis results. Section F describes the circumstances when an analyst might consider using default values, describes sources of these values, and describes the process for developing your own set of local values. The use of local default values are recommended since they can often improve accuracy of HCM planning analyses. A typical planning application of the HCM is to estimate the level of service of a large number of roadway lengths as part of a screening evaluation or as part of an agency's roadway system monitoring program. Generalized service volume tables can simplify this task. They present the maximum daily or hourly volume in a roadway facility that achieves a particular level of service. They are called generalized tables because they are constructed by applying standard default values to HCM methods and are applied to a large number of facilities of any given type, such as 4-lane freeways or arterials. The guide provides a few examples of these tables in Section G, based on default values derived from national data sets. However, it is also possible to create specialized service volume tables that are more representative of conditions found locally. The state of Florida, for example, publishes the Florida-specific service volume tables in their Quality and Level of Service Handbook. Section G describes when the service volume tables might be appropriate for an analysis and provides information about the 3 common sources of service volume tables, such as the FDOT Handbook. I'll now turn it over to Paul to take us through the remaining 3 parts of the guide.
Thank you, Aaron. I'm going to start now by talking about Part 2 of the guide, which covers median level analysis. As we mentioned before, this part of the guide is going to be probably the main point of entry for people who are already using the Highway Capacity Manual 6th edition. And the sections in this part should be very familiar to anyone who has used the HCM. Sections H through N each cover a HCM system element, such as a freeway, a multi-lane highway, or a signalized intersection. Section O, pedestrians, bicyclists, and public transit, cover methods for these modes across all HCM system elements where a method is provided. Finally, section P covers truck level of service. Sections H through N each have a similar outline, and we'll go through them here. The first three subsections provide an overview of what's covered in the section, remind the reader of the potential types of planning applications for which this section is appropriate, and lists the different analysis methods discussed in the section. Depending on the particular system element that we're covering, up to 4 different methods may be provided, each providing a different level of detail or covering a different aspect of performance. There can be a scoping and screening method. There could be a section analysis description applying the highway capacity manual with defaults. All sections provide a simplified HCM facility method, and the sections on freeways, urban streets, and signals provide information on calculating reliability performance measures. The final 2 sections in each of the Part 2 sections cover cross-references to Section O on multimodal techniques and provide cross-references to the case studies in Part 4 where the methods in that section are demonstrated. Now I'll go through each of the different types of methods that the planning guide provides. First, there are scoping and screening methods. These are applicable to freeways, multi-lane highways, 2-lane highways, and urban streets. And the scoping and screening sections describe how to either apply a generalized service volume table or to develop service volumes as part of creating a generalized service volume table. Current HCM users may be able to use the sections called section analysis using the HCM with defaults. These sections apply the HCM operations method, but use default values for many inputs to reduce the data requirements. A key requirement to be able to use these methods is that you have HCM implementing software in hand. Regular HCM users will almost certainly have this, but planners probably will not. In this section, the guide will provide information on what input data are needed to apply the method and will recommend default values for those inputs that can be defaulted. This particular subsection shows up in the sections for freeways, multi-lane highways, 2-lane highways, and urban streets. This table shows the example data requirements for multi-lane highways. It gives information on what's required to do an HCM section analysis, that is, an evaluation of the multi-lane highway between major intersections, as well as the input data required to do a facility analysis, which actually extends the HCM method beyond what's included in the current HCM, as the highway capacity manual only provides a section method. The facility method combines performance measures for sections and for the signalized intersections separating HCM sections to provide information on average speed, for example, across a long length of multi-lane highway. This table lists what input data are required and either tells the analyst that that particular input data item must be provided or suggests a default value if no local data are available for that particular input. It can be seen here to analyze an HCM section, 4 values must be provided by the analyst. Of these, 3, the hourly directional volume, the number of directional lanes, and the terrain type should be readily available to the analyst. In the case of the 4th item, free flow speed, the guide provides 3 progressively more detailed methods for estimating free flow speed, depending on the information available to the analyst. Every section in Part 2 provides a simplified highway capacity manual method. Now, most HCM operations methods require specialized software to implement them, but in developing the guide, it was recognized that many target users won't have access to this software. It was also recognized that using the HCM method with defaults may require more resources than are available or appropriate for a planning or preliminary engineering analysis. As a result, the guide prevents simplified methods that are HCM compatible but can be performed by hand or implemented in a basic spreadsheet. And these methods are capable of calculating multiple performance measures. In some cases, these methods are developed by running the HCM method the HCM method was run by the researchers in developing it, for example, the speed flow curves for freeways, and then a curve was created based on the results of that analysis. Therefore, instead of having to provide a lot of input data, you only have to provide a limited amount of input data to apply that particular equation or curve. As I said, simplified methods are available for all system elements. This table shows example data requirements for the simplified signalized intersection method. And you can see that you can calculate a variety of performance measures, including capacity, delay, level of service for motorized vehicles, the motorized vehicle component of multimodal level of service, and queue lengths. In this case, the only values that must be provided by the analysts are the number of turn lanes at an intersection as well as the traffic volumes by movement. All of the other input items can be defaulted, although of course if you have local data it's preferable to use that whenever it's available. Two sections within Part 2 cover additional topics. In the freeway section, there's a special subsection on adapting methods to evaluate advanced freeway management practices. And in the urban streets section, there's a method extension to cover overcapacity conditions. Section O provides methods for evaluating pedestrians, bicyclists, and public transit on a variety of HCM facility types. Now, not every combination of mode and facility type or system element is addressed in each of these subsections. For example, pedestrians on freeways doesn't make a lot of sense, and so that particular combination isn't covered in the guide. In some cases, the HCM doesn't yet provide a method for analyzing that particular combination. For example, bicyclists at roundabouts. But in those cases where the HCM does provide a method or a method that can be extended, that combination is provided in Section O. All of these methods provide a multimodal level of service result, but in many cases they also provide other performance measures such as average speed. Now, the Highway Capacity Manual doesn't provide a truck level of service measure, but such a measure was developed through a National Cooperative Freight Research Program project, incorporating truck level of service into the Highway Capacity Manual. And this measure this procedure has been incorporated into the planning guide. The truck level of service is based on the degree to which a roadway provides ideal truck conditions. And those are specified as a roadway that can be used by trucks with legal size and weight loads, no at-grade railroad crossings, roadways provide reliable truck travel at truck free flow speeds, and low cost that is having no tolls. So a roadway that meets all of these conditions we consider to have truck level of service A. As a roadway does not meet all of these conditions, then its level of service goes down. Now we'll look at Part 3 of the guide, which covers high-level analysis methods. Part 3 contains 3 sections. One dealing with corridors, Section Q, Section R, which covers areas and systems, and Section S on roadway system monitoring. Section Q presents a quick estimation method for assessing corridor capacity. You can also use methods in Section R if you want a more detailed assessment, or you can use the facility-specific methods that were found in Part 2. The performance of a freeway arterial corridor system and its components are often estimated through a travel demand forecasting process combined with either a microscopic or macroscopic traffic operations model. This process requires a variety of inputs and outputs which the HCM can provide, including capacity, queues, delay, travel speeds, and level of service. And Section Q provides information on how to develop those inputs and outputs. Now, the Highway Capacity Manual stops at the facility level, that is, a 10 to 15 mile maximum section of freeway or a several mile section of urban street. And it doesn't really go beyond looking at a single facility to looking at how multiple facilities work together as a system. However, area and system-wide analysis is something that is often looked at as part of a planning study. The HCM can be applied during a travel demand modeling process to both develop more accurate capacity inputs to the model and to generate additional performance measures not directly output by the model. And Section R provides guidance on both of these aspects of area and system-wide analysis. At a federal level, looking at roadway system monitoring is becoming more and more important. Section S provides guidance on identifying and diagnosing travel time reliability and capacity problems. The method presented in this part of the guide assumes that the agency has access to archived average travel times by road segment and by time of day. It presents information on the travel time index, the ratio of actual to free flow travel time, and uses it as one indicator of congestion problem spots. Next, I'm going to look at the 3 case studies provided with the guide that show how the guide's methods can be applied. There are 3 case studies. The first case study looks at a freeway master plan effort for a 70-mile section of freeway. Case study 2 looks at how the methods in the guide can be applied to analyze an urban street corridor where bus rapid transit is being proposed, including converting one travel lane into a bus-only lane. This case study also looks at the pedestrian and bicycle operations impacts of developing the bus rapid transit line and the associated roadway changes. Finally, case study 3 presents the application of the guide's methods to a long-range transportation plan. We'll start by looking at case study 1, a freeway master plan. This master plan, which is inspired by an actual project, covers a 70-mile stretch of US 101 in San Luis Obispo County on California's Central Coast. US 101 in the county is mostly a 4-lane freeway, but it has some multi-lane highway sections where you have at-grade access to the highway at intersections. And there's also a 6-lane section where the freeway goes over a 7% grade over a hill. The objective of this master planning effort is to identify current and future problem areas and to prioritize projects for future capital programming. The case study consists of 7 example problems that demonstrate how you might proceed through the guide, applying it to this freeway master plan, starting at a very high level and then proceeding to a more detailed medium level of analysis. So example problem 1 starts by demonstrating a screening analysis. So we have a 70-mile stretch of freeway and we want to narrow it down to only those sections that may have problems in the future. So to do this, we split the facility into what we call super sections. on the basis of similar demand volumes, terrain, facility type, and number of lanes. So we're looking at, is the supersection urban or rural? Is it level or hilly terrain? How many lanes does it have? Is it a freeway or multi-lane highway? And where the different elements change, then we create a new supersection. And so if you look at the map, you can see we have 9 supersections, and these range from 3 to 13 miles in length. This example problem then uses service volume tables to look at where a supersection may exceed level of service D or level of service E, and it will flag these supersections for more detailed analysis. If a supersection meets the service volume for level of service D or level of service C or better, then it's assumed that it will operate well in the future, and there's no need for more detailed analysis. Example problem 2 takes one of the supersections that is identified as being potentially problematic and looks at it in more detail. This is supersection C, which is a 5-mile stretch of rural freeway connecting the cities of San Luis Obispo and Pismo Beach. In this step, supersection C is split into 7 sections between ramps. So every time we have an on-ramp or an off-ramp, we create a section boundary. Next, we identify what each section's per lane capacity is. Next, per lane demand volumes are compared to per lane capacity. Places where the demand exceeds the capacity are determined to be bottlenecks, and the method meters demand to the downstream section. This is in contrast to a typical travel demand forecasting model, which will assign all of the demand to a downstream section, even if the roadway is not physically capable of delivering all of that demand. The planning method presented in this guide does meter the demand from one section to another. These bottlenecks that are identified as part of this step can be flagged for further analysis, for example, to analyze mitigation options, which is the subject of the final example problem in this case study. Example problem 3 demonstrates how to calculate speeds and travel times through the supersection. This is first done at a section level between ramps, and then the results are aggregated to create speeds and travel times for the section as a whole for 15-minute time intervals. The only input requiring for estimating speed is the demand to capacity ratio, which was already determined as part of example problem 2. In order to determine the travel time, you also need to know the section length, but this should be information that's readily available to the analyst. The results of the analysis can be tabulated or shown in a contour diagram such as the one shown on the screen here. Here it can be seen that section C2 experiences congestion problems for just 15 minutes out of the peak hour, but that section C4 is a bottleneck and experiences congestion problems throughout the peak hour. Example problem 4 shows how to estimate level of service. Now, in the HCM, freeway level of service is based on density, which is demand divided by speed. And we've already determined speed, and we know what the demand is. So the process in this step is to adjust demand from vehicles per hour to passenger cars per hour to account for the effects of trucks in the traffic stream. Once we have that, then it's just a simple calculation to determine density. Again, the results can be tabulated or plotted as in the form of a graph, such as shown here. And here it can be seen that the supersection generally operates at level of service E or F throughout the peak hour, confirming the earlier screening analysis that was done as part of example problem 1. Example problem 5, queues are estimated for each section for each 15-minute time period. If the queue length exceeds the section length, the section is considered to be 100% in queue. The planning method does not propagate queues upstream. And if a section is identified to be 100% in queue, this means that more detailed analysis would be required if you want to identify how far back the queue extends into an upstream section. In example problem 6, we look at ways of calculating different measures of the section's reliability. We can calculate an average facility speed as vehicle miles traveled divided by vehicle hours traveled. We can identify the maximum demand to capacity ratio on the facility. We can estimate the 95th percentile travel time index, and we can estimate the percent of trips under 45 miles an hour. Now, after the guide was finalized, the Federal Highway Administration came out with proposed rulemaking for its performance management measures for roadways, including reliability measures. And the measure that they're proposing is the level of travel time reliability, which is the 80th percentile travel time divided by the 50th percentile travel time. The guide does not provide those particular travel times, but an addendum to the guide, which is available on online volume 4 in the same place where you can download the guide itself, provides information on estimating the 50th and 80th percentile travel time indexes, from which the level of travel time reliability can also be estimated. The method for calculating these measures comes from the same source as the method presented in the guide for calculating the mean and 95th percentile travel time indexes. Example problem 7 for case study 1 looks at the effect of adding an auxiliary lane to the bottleneck section, to section C4. So basically adds an extra lane in that section connecting the on-ramp to the off-ramp. The calculations that were performed in examples 2 through 5 are repeated, and it's found that the auxiliary lane removes the bottleneck at section C4, but as a result, more demand is able to proceed downstream, and sections C5, C6, and C7 then operate at or close to capacity. So in either scenario, we have at least one section that operates at level of service F. But by looking at other performance measures such as facility speed, density, queuing, and maximum demand to capacity ratio, we can see that the proposed mitigation, adding the auxiliary lane, improves the operations of the facility across a variety of performance measures, even though it still operates at level of service F. Now let's move on to case study 2, which is looking at an arterial bus rapid transit project. Again, this is a study or a case study that's inspired by a real-world project, but again, we've made changes to the conditions to better fit the examples that we want to present as part of the case study. In this case, a 14-mile BRT line is proposed running through the East Bay of California through Oakland. The entire line contains 110 signalized intersections, which would be a lot to have to analyze if you applied the full HCM operations method or wanted to go to simulation. This case study demonstrates the urban street and multimodal planning methods. The basic project as assumed for this case study would remove one travel lane in each direction to create exclusive bus lanes. It would also remove parking to create a bicycle lane and would widen the sidewalks somewhat. Example problem 1 presents a screening analysis. This is a very similar process to what we've already seen for freeways, in that we divide the facility into supersections on the basis of demand volume, speed limit, median presence, and number of lanes. We then apply service volume tables to identify which sections would operate at level of service D with the project and which ones would operate worse than level of service D. And as a result of this analysis, we identify 6 of the 10 supersections would operate worse than level of service D with the project as proposed. The remaining example problems then focus on one supersection to demonstrate some of the other methods for evaluating an urban street. Example problems 2 and 3 focus on signalized intersections. Example problem 2 looks at intersections with protected left turn phasing, that is, where a green arrow is provided to left turning vehicles, while example problem 3 looks at permitted left turn phasing, where only a green ball signal is provided and automobiles have to wait, or drivers have to wait for a gap in traffic before making their turn. These case studies look at how you can estimate future left turn phasing if it's not already been determined, how to identify lane groups, how to develop equivalent through passenger car volumes, how to calculate critical lane group volumes, and finally how to calculate an intersection volume to capacity ratio. Example problem 4 shows how to determine auto speeds and level of service. It also demonstrates how bus speeds can be evaluated for the bus rapid transit route. In this case, we look at the capacity of each intersection approach, determine the delay by approach, and then combine or aggregate the results for each section to determine the auto speed and level of service for the supersection as a whole. Example problem 5 looks at queuing, and here we're estimating average and 95th percentile queues by major street approach. This kind of application can be useful for identifying potential queuing hotspots where queues might back into adjacent intersections or might block major driveways. Example problem 6 demonstrates the multimodal methods presented in the guide. And here we're comparing before and after pedestrian, bicycle, and transit level of service. In the before condition, we have 7 to 14-foot sidewalks, depending on the section, 2 general-purpose travel lanes and 1 parking lane in each direction, and 6 local buses operate on the street in each direction per hour. In the after condition, we have 1 general-purpose travel lane, 1 bus lane, and 1 5-foot bicycle lane in each direction. The remaining 3 foot is used to help create a 5-foot landscape area. And for transit service, we have 5 BRT buses, which are only making 1 stop within the whole supersection, as well as 4 local buses per hour, which generally stop within each section. Example problem 6 shows how to perform the calculations for each of the modes. And we find out that pedestrian level of service improves from mostly level of service B to level of service A. This is due to the greater separation that the pedestrians experience from most of the motorized traffic, as both the landscape buffer and the bus lane greatly improve the level of service. Pedestrian level of service is particularly sensitive to adjacent traffic volumes, so the farther away pedestrians are separated from traffic, then the better the level of service. The bicycle level of service improves from mostly level of service E to level of service A, and this is largely due to the fact that there was no bicycle lane in the prior condition, but there is a bicycle lane in the after condition. In addition, we have a bus lane with only 9 buses per hour that provides low motorized vehicle volumes in the adjacent lane. So the combination of those 2 items greatly improve the bicycle level of service. At the local stops, the bus level of service stays at level of service C. Although at these stops, the frequency of service goes down from 6 buses per hour to 4 buses per hour, the less frequent service is offset by improved bus speeds. At the 1 BRT stop in this section, the bus level of service improves the level of service B due to the improved frequency and the improved travel speed. Now let's move on to case study 3, a long-range transportation plan. This particular case study shows how to develop free-flow speeds and roadway capacities as part of an input to a travel demand model. This example problem shows how planning techniques can be applied to develop improved inputs to the travel demand model and how they can be used to post-process model outputs to generate additional useful performance measures. Example problem 1 shows how an analyst can develop a lookup table that provides an HCM-based free flow speed and capacity for different combinations of facility type and other factors of interest, such as area type, terrain, and specialized facility types. Each link in the travel demand model is then assigned a free flow speed and capacity from the lookup table on the basis of the link's particular combination of these characteristics. Example problem 2 shows how HCM-based speed flow curves can be developed and incorporated into a regional travel demand model. This process can also be used to post-process model output when more accurate speed estimates are desired as inputs into air quality and noise models. Example problems 3 and 4 demonstrate how travel demand model output can be post-processed to generate additional useful measures of operational performance. Example problem 3 demonstrates the calculation of density, queuing, and delay, while example problem 4 demonstrates the calculation of measures of travel time reliability. So where can you get the planning guide? The guide can be downloaded from HCM Volume 4 at the address www.hcmvolume4.org. A free one-time registration is required. The guide can also be downloaded from the National Cooperative Highway Research Program website, but we recommend that people use the HCM Volume 4 site because additional resources will be available in the future from this page. And right now, 5 spreadsheet computational engines are provided on Volume 4 that help implement some of the guide's methods. So although all the methods that we've demonstrated can be implemented by paper and pencil using worksheets provided in the guide, we also provide spreadsheets to help speed up the process further. They're particularly helpful if you have multiple intersections or multiple sections of a facility that you want to evaluate. In addition, there's a project underway to develop additional outreach and training materials to support the guide, and these materials will be posted on Volume 4 over the course of 2017 as they are completed. So to wrap up, the guide provides a resource for both HCM users and planning professionals to conduct quick back-of-the-envelope evaluations where a full HCM analysis is neither needed or necessary, and neither is simulation. The methods in the guide maintain consistency with the HCM throughout the project development process because they are based on actual HCM operations methods. And the guide demonstrates how methods from the HCM, or bits and pieces of them, can be incorporated into planning tools, whether to develop inputs used by planning models, to improve the accuracy and consistency of computations performed within those models, or to post-process model outputs to create additional performance measures. And with that, I'll turn it back over to Courtney.
Great, thank you so much. So now we have a few minutes to type your questions into the question pod. I'll give everyone about 2 to 3 minutes. If you're hosting a webinar, please collect your questions from the multiple attendees at your site, and I'll start reading off the questions here momentarily. I just want to give individuals a chance to type in their questions before we begin. Okay, so we have a few questions that have come in so far, so I'll go ahead and get started. We don't have as many questions as we did for the first webinar, but I'll go ahead and begin. Why did it say none for truck LOS. So I think this is when Aaron was speaking. Do you recall what this attendee is referring to, Aaron?
Yes, I think they're referring to our reference to case studies and where it is. So we talked about the truck level of service, and it can be found in section P, but then it said there are no case studies. And I believe just that there's a lot of different methodologies, and we couldn't incorporate all of them into the case studies, so truck level of service was not one that's provided as an example application, but there is a methodology for it.
Great.
And I don't know if Paul has any more to add to that. But.
No, I think that you answered that well. You know, as a member of the Highway Capacity Committee, I'm hoping that the committees will take this on as a project in the future to develop additional case studies for the guide. I can't promise that will occur, but that's something I think we hope will occur. But as Aaron said, right now there's only so much that we could include in this first edition of the guide, and that was one thing where it wasn't possible to develop a case study.
Great. Okay. So the next question that we have is, how many intersections were surveyed for default values?
Well, I think the default values that are presented in the guide come from the Highway Capacity Manual, and it's based on, it really depends on, for any particular input, depends on what the original source of it was. So I can't say that there was any particular number that was analyzed. It would probably be a good question to ask during the signalized intersection webinar. What we do recommend is that whenever you have local data available, that you use that, and the guide does provide information on developing local default values. So if you have information on local signal timing, for example, that would be something that the guide would recommend that you would use in favor of the national default values provided in the HCM.
Great. Okay, what's the LOS for the passenger vehicles in the multimodal case study?
Well, if you go through that case study, what you find is one intersection operates at level of service F. The other intersections operate at level of service D or better, I believe. And then the overall facility level of service is F in the peak direction, and I think it's D in the off-peak direction based on speed. So what the case study would be telling you is that the proposed configuration of taking away a travel lane to provide a bus lane, at least at that one intersection, is going to create operational problems. And then you could take the process further by either applying the planning guide to look at potential mitigation options, or at that point you would go to a full HCM operations analysis and simulation to look at different alternatives for that one intersection. What you have found out is that the other 5 intersections within that particular supersection, they work fine, and it's just this one intersection that's the problem spot.
Okay. Will all these engine computational tables be incorporated in the Florida MCTRANS HCS?
I guess I'll take a stab at this one. I would say that these tables are going to be available to HCS in the MCTRANS Center, but I'm not sure if they're going to actually incorporate them. I think HCS generally stands on the side of kind of implementing the HCM methodologies itself. They do have things like art plan, I believe, in HCS itself that may be where these methodologies show up. But as to whether they'll do it, it's really a decision for MCTRANS Center.
Okay, and then the next question, does the new freeway LOS method and or truck LOS method consider truck platooning? Okay,
I'll take that one. The freeway level of service method doesn't consider truck platooning specifically. It does account for the amount of truck traffic on the facility, and the HCM itself has updated methods that particularly look at the impacts of trucks when you have a relatively low volume of trucks, but you have extended steep grades that they're going up because they have a disproportionate effect on the overall operation. But they don't consider truck platooning per se. The truck level of service method is looking at the quality of service provided by the roadway from the truck or freight shipper point of view. Does it meet the needs of the shipper from the standpoint, can their trucks operate on that road? How reliable is the service provided on that road? How much does it cost to use that road? Things like that.
Great. For the BRT analysis, is ridership a consideration or person trips a consideration in the evaluation?
Well, the HCM is not a demand estimation model or tool, so we really don't get into ridership or person trips. It would certainly be something that you could look at. In addition to the operations, you could look at how might ridership change with respect to the improved speed on the facility, for example. And if you want to do that, then another resource, the Transit Capacity and Quality of Service Manual, can help you out with that. It provides some elasticity factors from research looking at how both frequency and travel speed affect ridership. That's built in indirectly into the method for calculating transit level of service. But if you want a direct estimation, it's you can go to the Transit Manual for that.
Okay. On the freeway supersection analysis, how does the guide account for the influence area of an entrance ramp versus an exit ramp versus auxiliary sections?
Okay, well, unlike the HCM where there's a defined influence area before and after the gore of the ramp, that's used to define what a ramp segment is, or in this case what a weaving segment would be. The planning guide method simplifies it into sections in between the entrance ramp and the exit ramp. So there are no influence areas. And instead it provides a conservative estimate of what the capacity would be within that section.
Okay. The next question is a spreadsheet freeway planning tool applicable to locations where we have multiple hours of LOS-F?
The spreadsheet tool is really designed for a 1 hour evaluation. You can certainly extend it to look at multiple hours. Keep in mind that if you have multiple hours at level of service F, that you're going to have a lot of Q spillback issues. And in that case, using the FreeVal computational engine that's included with the HCM 6th edition would probably be the better tool to use. But there wouldn't be anything stopping you from basically cutting and pasting the sections in the computational engine that's provided with the guide to look at additional hours.
Great, thank you. We have a few more that keep coming in. For corridors that are congested and that have peak spreading, can the model handle multi-hour peak period analysis? I may have read that. I think I'm missing a word there. For corridors that are congested and that have peak spreading, can the model handle multi-hour peak period analysis? Okay, that makes sense.
I think for freeways, that's kind of similar to the last question that was asked, that the computational engine won't do that for you. The method itself, there's nothing that prevents it from looking at multiple hours, but you would probably also want to consider using FreeVal at that point, or another tool that implements the HCM operations method?
I would say the planning method itself would give you a good idea of how many hours you need to consider, because it'll indicate that. But then you really need to jump back into the full HCM method to figure out the real impact of all that.
Okay. All right, the next question. LOS is a very popular MOE, but it's a challenge to represent LOS when you study a very long corridor over multiple hours. Is HCM looking into how LOS can be simplified?
Well, there's an ongoing discussion within the committee about what is the future of level of service. At the TRB annual meeting, the committee's sponsoring a session on this very topic, considering that, for example, California is moving away from level of service as a measure. The guide takes the position that we want to provide you with a range performance measures, and you can decide what's the most appropriate measures to include as part of your analysis. In many of the cases, for facilities, urban street facilities or freeway facilities, if you're looking at extended length of facility, you're getting average speed and travel time as key performance measures that are coming out of the analysis.
Okay. Is there a micro simulation as part of HCM 6?
The Highway Capacity Manual 6th edition provides sections for each system element, such as a freeway facility, discussing cases where simulation might be a better tool than the operations method to evaluate the facility. For example, there's some limitation of the HCM method that simulation can address, the HCM can't. It also provides information on using both methods hand in hand, the HCM operations method and simulation, and making sure that the performance measure definitions that simulation is producing are compatible with how the measures are defined by the HCM.
Okay. Mid-level analysis is often used with long-range predictions to get 20-year life estimations for numbers of lanes, etc. Is there guidance for this in the guide? And I can read that one more time. Mid-level analysis is often used with long-range predictions to get 20-year life estimations for numbers of lanes, etc. Is there guidance for this in the guide?
I would think this would be a function of kind of using a service volume table. If you're projecting volumes out to 20 years in the future, service volume tables would give you what type of facility and what its capacity could be. So if you know it's going to be 6,000 vehicles per hour, and level of service C for a 6-lane facility, for example, would cover that, then you'll know what your level of service would be.
Okay. Looking into the future, does the model have parameters to capture operational effects on connected and autonomous vehicles?
I think if you want to do that, you would need to start with the Highway Capacity Manual method. I would expect as the Highway Capacity Manual, as more research is done, and some of these questions about what are the impacts of connected and autonomous vehicles on the roadway system are answered, they would first be incorporated in the HCM operations methods, and then they would make their way into the planning methods. But we really don't know at this point what the impacts will be, and depending on who you ask, it can go either way in terms of capacity. There are some that will say that because of the technology that cars will be able to operate closer together on the freeway and therefore you'll get more capacity, and there are others who will say that from a safety standpoint, to make sure that everything operates in a fail-safe manner, that you may have to have larger spacings in between vehicles. And so until all of that kind of shakes out and we see how things develop, you can kind of play what if with the Highway Capacity Manual by using different saturation flow rates that reflect different inter-vehicle spacings. But we don't really know for sure how it's all going to play out until I think we get a few more years down the road.
And picking up on what Paul said, I think a lot of the methodologies in HCM are applicable, but what we might see change with connected vehicles or autonomous vehicles is more of the default values or how they're derived in the first place, because those are likely to change.
Great. Okay. Would you believe the, are there any recent or current projects where these methods have already started being implemented? What can you share about which regions of the country, agencies, and consultants have been using these new methods? I can read that question one more time. Are there any recent current projects where these methods have already started being implemented? Can you share with us which regions of the country, agencies, or maybe consultants where they have been using these new methods?
Well, the planning guide itself only came out in August, so it's probably not likely that many people have started applying it yet. But for something very similar to the concept in the guide, you can look to Florida, because they have their Florida Quality Level of Service Handbook, which is very planning focused. And that is widely used throughout the state. The DOT says identifies what kinds of studies should use that particular guide. And so our planning guide that comes with the Highway Capacity Manual kind of takes that a step further by looking at a broader range of Highway Capacity Manual methods and more national values and guidance on providing or developing your own local default values, whereas the Florida guide has studied Florida conditions very extensively, and so its default values are very Florida specific.
An example of that, I guess in Oakland, we're looking at doing some bike ped planning projects that are going to have a service volume table. So we had the choice of maybe using a national default value, using ones from the FDOT book, or using more local specific ones. After talking with the City of Oakland, for example, we determined that it's probably not good to use the FDOT tables because it's kind of hard to explain why we're using FDOT tables in California. The national tables would probably work, but Oakland wanted something that's a little more adaptive to what their facilities are. So essentially, we are going to be creating a generalized service volume table for Oakland specific to deal with their bike projects.
Great, and we have about one more question that came in. Would you believe the guide methods provide acceptable support for operational analysis required for interstate access point approval requests from Federal Highway? I'll read that question again. Would you believe the guide methods provide acceptable support for operational analysis required for interstate access point approval requests from Federal Highway? Do they provide acceptable support for operational analysis required for interstate access point approval?
I would say that's... Go ahead, Aaron.
Go ahead, Paul. Well, I'm not up to exactly on what Federal Highway policies are for access points. Where I would think the guide would be useful is kind of as a preliminary guess to see if you even want to go into that, a more detailed analysis to see if it would be relevant. I mean, if you know you're not going to get through it with your planning level, then you can save some money by not diving into the full ops analysis.
Yeah, I would say probably unless, until such time FHWA says that yes, you can use it, then probably not, even though it might be applicable.
Okay, fantastic. So I guess that wraps up our Q&A, and that brings our webinar close to an end. So before we close out here, I will go over how to earn PDH credit for